Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be going over part 1 on how to verify trigonometric identities. The instructions for the examples we're going to be working on today are as follows. We have to verify the given trig identities. Okay, so let's start with question number 1. Cosine x secant x is equal to 1. Now, when we're verifying trig identities, the goal is basically to make both sides of the equation identical. If we can accomplish that state, then we would have shown that the trig identity that resulted in that conclusion is in fact correct. Okay? Alright, so if you take a look at this equation that we have right here, 1 is already in its simple form. We want to examine cosine x secant x to see if we can simplify it to get 1. Now, when you're working on verification of trig identities, if you have just product or quotient of trig functions and their powers, the easiest way to simplify them is to express every function as sine or cosine. Okay, that makes it very easy to carry out your reduction by cancellation. So cosine is one of the parent functions. How about secant? For secant, you want to recall the reciprocal identity that secant x is equal to 1 over cosine x. So we can use this identity to replace secant. So we have cosine x times, instead of secant, we use the reciprocal identity to express secant as the reciprocal of cosine. So the question is this product right here in its simplified form, is it equal to 1? So let's simplify a little bit further. You can divide out. Cosine goes into cosine 1, and cosine x goes into cosine x once. 1 times 1 over 1 is 1. Is 1 equal to 1? The answer is yes. So we've been able to show that this trig identity is in fact correct. Alright, let's take a look at question number 2. What if we have cosine square x divided by cotangent square x is equal to sine square x? So if you look at the left side of our equation, we have the quotient of the powers of two trig functions. Whenever you have scenarios like this where you just have to simplify by division, you want to express all the trig functions as sine or cosine as indicated in number 1. So cosine square x is already cosine square x. Sine square x is already one of the parent functions. Let's focus our attention on cotangent square x. Can we express this function cotangent as a combination of sine and cosine, or either sine or cosine? For that, we have to recall the quotient identity. So I'd like you to recall the fact that cotangent x, or theta, is equal to 1 over tan, or cosine theta divided by sine theta. Okay, so let's go ahead and carry out the substitution. Cosine square x, we bring that down, divided by cotan square x is the same thing as cotan, the entire function raised to the second power. Okay, so let me write it in this format for you. So cotangent square x, if I want to replace it with cosine over sine, what we're going to have is cosine x divided by sine x square, because the cotangent function is being squared. So the question is this quotient expression we have on the left side equal to sine squared x? Now we have a complex fraction here. Let's go ahead and simplify that. But before we simplify, let's use the quotient of a power property of exponents to address this squared of the quotient. So we'll have cosine square x divided by cosine square x divided by sine square x. Basically, we square the numerator and the denominator. Okay? So is this equal to sine square x? Is it? Now to finish this off, we can drop change flip. So you drop the numerator, cosine square x, and you multiply it by the reciprocal of the denominator, sine square x, over cosine square x. So is this equal to sine square x? Is it? If you examine what we have here, you can put a 1 underneath cosine square x. We can divide out cosine square x goes into cosine square x once, and then cosine square x goes into cosine square x once. And what does this imply? Well, we have is sine square x equal, is it equal to sine square x? Absolutely. So achieving this true statement, we've been able to show that the original trig identity is in fact correct. Alright, let's go ahead and take a look at question number 3. For question 3, we have the identity sine square alpha minus cosine square alpha is equal to 2 sine square alpha minus 1. So is this a true identity? Let's go ahead and verify this one. Now, when you have a sum or difference of squares of trig functions, you want to think along the lines of the Pythagorean identities. Okay, so how can we use the Pythagorean identities to make to end up with an equality? Okay, so let's take a look at what we have here. If you look on the right side, you notice that you have only sine. On the left side, we have cosine and sine. So the question is, can I express cosine square x in terms of sine using the Pythagorean identities? Let's step to the side first and recollect what the Pythagorean identity that relates sine and cosine is. So it's sine square theta plus cosine square theta equals 1. Now if I get cosine isolated by subtracting sine square theta from both sides, what I will end up with is cosine square theta equals 1 minus sine square theta. So if I want to express cosine square theta using sine, I can use 1 minus sine square theta to accomplish that goal. So what I'm going to do is go back to this statement. We have sine square alpha minus, instead of cosine, I will replace it with what it's equal to from the Pythagorean identity, which is 1 minus sine square alpha. Okay? Question is that equal to 2 sine square alpha minus 1? Now we focus our attention on the left side, see if we can manipulate it to get the right side. Now what we're going to do is we're going to go ahead and distribute this negative to 1 and sine square theta. So that yields sine square alpha minus 1. Minus times minus is plus, plus sine square alpha. The question is it equal to 2 sine square alpha minus 1? Now we have two like terms here, sine square alpha and sine square alpha. If you add them together, you end up with 2 sine square alpha minus 1. Is it equal to 2 sine square alpha minus 1? Is it? Absolutely. So we've been able to show that the original identity is in fact correct. All right, let's take a look at question 4. So what if we have the following identity and we're to verify if it's correct? So what if we have sine to the fourth of x is equal to sine square x times 1 minus cosine square x? Okay, so now look on the right side, you have a difference and the square. So whenever you have a difference and a square of squares of trig functions, always think along the lines of the Pythagorean identity. Okay, so hopefully that could help us here. On the left side we have only sine. So our attention should be focused on this component right here. Can I use the Pythagorean identity to express this quantity as a power of sine? If I can do that, then I can then shift my attention on trying to make both of them equal to each other. Okay, so let's go back to our Pythagorean identities again. We remember that sine square theta plus cosine square theta is equal to 1. What happens if we subtract we already did this before. Subtract sine square theta from both sides. Alright, if we do that, we have cosine square theta being equal to 1 minus sine square theta. That doesn't help me out. What I need is I need 1 minus cosine square theta. So let's do something different here. How about we subtract cosine square theta from both sides of the equation? Okay, so if I subtract cosine square theta from both sides of the equation, I'll end up with sine square theta equals 1 minus cosine square theta. Okay, now this is much better because it enables me to express this difference of squares as a power of a sine function. So we have only sines on the right side of the equation. Okay, so we have sine to the fourth x. Is it equal to sine square x times, replace this difference of squares with sine square x? Is it the same? Sine to the fourth x, using the product of powers property of exponents, we can multiply these two. We have sine to the 2 plus 2. When you're multiplying powers, you add the exponents, right? Powers with the same base, the product is basically the sum of the exponents. So the question now is sine to the fourth x, is it equal to sine to the fourth x? The answer is yes. So this shows clearly that the original identity is in fact correct. Alright, let's take a look at the next problem. Question 5. Now what if we're to verify if this identity sine square x plus 2 is equal to 3 minus cosine square x is in fact correct. Now in this case we have sums and differences, and we also have squares of trig functions, sine square x and cosine square x. So what approach do you think we want to use here? You want to use the Pythagorean identities. Okay, anytime you have pluses and minuses on the squares of trig functions, you want to think along the lines of your Pythagorean identity. Now I have sine square x on the left side and cosine on the right. Is there a way I can use the Pythagorean identity to express cosine in terms of sine? So let's go ahead and call up our Pythagorean identity again. So we all know that sine square x, or sine square theta plus cosine square theta, is equal to 1, but I have cosine square theta here, so if I get cosine square theta by itself, cosine square theta is basically equal to sine squared theta. Okay, so let's bring down the left side. Is sine square x plus 2, is it equal to 3 minus, so we take out the cosine and replace it with what it's equivalent to, which is 1 minus sine square x. Is this a true statement? Is this left side equal to the right side? Well, let's simplify it further, okay? So sine square x plus 2, is it equal to, now we're going to distribute this minus, okay? So we have 3, so minus goes to the 1, and it goes to the sine square x. So 3 minus 1, minus times minus is plus, plus sine square x. Is this a true statement? Simplify it a little bit more. Sine square x plus 2, is it equal to 3 minus 1 is 2 plus sine square x? The answer is yes, right? Because we know that the addition operation commutes. So 2 plus sine square x is the same thing as sine square x plus 2. Okay, so we've been able to show that this identity is in fact correct. Alright, let's take a look at question number 6. Now what if we have the identity 1 minus secant x times 1 plus secant x equals negative tan square x? Is this identity true? So let's go ahead and verify. Now what we're going to do is take a look at what we have. We have a sum and a difference of trig functions here with 1. So we should be thinking along the lines of implementing the Pythagorean identity somewhere in the simplification process in order to achieve equality. Alrighty? So here we have a product. Why don't we just go ahead and distribute this out? Okay? So we're going to multiply first, outer, inner, and then last. Okay? Alright, so let's go ahead and carry out our multiplication. 1 times 1 is 1, plus 1 secant x minus secant x, minus times minus, minus times plus, sorry, is minus secant square x. Is this equal to negative tan square x? Is it? Now notice the middle terms cancel. Hopefully that doesn't surprise you, because what we had here initially is a difference of squares. So what is a plus b times a minus b? We all know what that is. We studied that in Algebra 1. The expanded form of a difference of squares. A minus b times a plus b is equal to a square minus b square. Okay, so we shouldn't be surprised that we're getting 1 minus secant square x. Is this equal to negative tan square x? Is it? Now, let's think about our Pythagorean identities for tan and secant. If you remember your identities, you will know that 1 plus tan square theta is equal to secant square theta. So I want to express 1 minus secant square theta in terms of tan, right? So we have this situation right here. Now, if I want to get tan square theta by itself, I subtract 1 from both sides. So I have tan square theta is equal to 1 minus secant squared theta. Oh, sorry, I made a mistake. Let me make a correction here. When I subtract 1 from both sides, I should get 1, secant square theta minus 1. Okay, so tan square theta is equal to secant square theta minus 1. Okay, so now if you examine what we have here, we have 1 minus secant square theta, and over here we have secant square theta minus 1. So can I simply reverse the order of a difference? Does the subtraction operation commute? The answer is no. Okay, so what if I go ahead and say, alright, I want to rewrite this as secant square x minus 1. Whenever you switch the order of a subtraction or a difference, you have to introduce a negative. Okay, because when I distribute this negative back in, I'll end up with negative secant square theta plus 1. Okay, so you don't simply just switch differences. You can switch sums or products because they commute, but difference does not commute, hence you cannot just simply switch the order of a difference. You have to introduce the minus anytime you switch a difference, okay? So is this equal to negative tan squared x? Is it? Now we can use the identity and replace secant square x with tan square. We can replace secant square x minus 1 with tan square x using this identity that we have right here, a variation of the Pythagorean identity for tan and secant. So is that equal to tan square x? It certainly is. This answer is correct. Alright, let's go ahead and take a look at question number 7. Now what if we have cotangent square x times secant square x minus 1, is it equal to 1? Now if you examine what we have on the left side, we have a difference and a square of a trig function, so we want to think along the lines of implementing the Pythagorean identity. Now secant square x, can I express it as a trig function that can have something common with cotangent, something I can cancel out or reduce with cotangent? Now if we go back to our Pythagorean identity with secant square x, we know that 1 plus tan square x is equal to secant square x. Okay, so we have to recollect this fact. Now if I subtract 1 from both sides, I'll have tan square x is equal to secant square x minus 1. So I can replace this secant square x, so I'll bring down cotangent square x times tan square x. Okay, is it equal to 1? Now let's see how we can simplify this. Using our reciprocal identities, we can express cotangent square x as the reciprocal of tan. So you also want to recollect the fact that cotangent theta is equal to 1 over tan theta, right? So cotangent square x can be expressed as 1 over tan square x. So it's 1 over tan square x times tan square x. Is it equal to 1? Can divide out the tan square x's. 1 times 1 is 1. Is 1 equal to 1? It certainly is. So we've been able to show that the original identity is in fact correct. Thanks so much for taking the time to watch this presentation. I really appreciate it. If you found the contents of this tutorial helpful in your study of trigonometric identities, do give us a thumbs up. Your positive feedback is very valuable to us. If you have any questions or comments about the contents of this presentation, just place your questions in the comment section below and we'll be more than glad to respond. We update videos to our YouTube page on a consistent basis, so do subscribe to our channel for updates to other pre-calc tutorials such as this. More clips can be found on mathcodeserve.com. Thanks again for watching and have a wonderful day.